once again. Now today we got Professor Geert Leus from Technical University of Delft, Netherlands, to give us a talk. He's yet another very outstanding researcher in signal processing. His research spans a broad spectrum of areas, which includes communications. Now, actually, I myself know a little bit more on your research on communication. I'll talk more about it later on, as well as sensor network, spectrum sensing, and more recently, distributed and graph signal processing. Geert got his PhD at Catholic University of Leuven in Belgium. He was also a visiting researcher previously with Stanford and also with University of Minnesota. And what his research, of course, is very highly cited, receive a lot of attentions. He also contributes significantly to the society. Now, there are many things you can find in his CV, but I try to mark a few of them. He was SPCOM TC chair. He recently is a editor-in-chief of URSIP signal processing, which I believe is a lot of work. We can talk a little bit more later on how hard it is. And he also received 2 Best Paper Award, one Young Author Best Paper Award in 2002, another 2005, IEEE Distinguished Lecture 2018 and 19, and of course IEEE Fellow. Now, finally, before I pass it to Geert, now I remember this paper extremely well. Okay, you may not know it because I never mentioned it. Now, that was the time I was still a postdoc fellow or something, struggling to survive and try to find some interesting thing to work with. Now, I never told you that this paper actually had a lot of influence on me. I think another organizer, Zhonghui Zhang, would also agree, because later on I went to Taiwan to start my career, and one of the first project I gave to Zhonghui was related to this topic. And also, this paper received Best Paper Award. But by the way, I mentioned this not because it received Best Paper Award. It's really because it has some influence on me. Okay, so without further ado, Geert, the floor is yours.
Thank you for the nice introduction and for bringing up this paper. Actually, there's a lot of stories behind this paper, but I'm
Lee told me that. I know that.
Details about that.
Yeah, we'll talk about it in the future.
I was actually a reviewer of that paper, but that's a long story. But I was a reviewer of my own paper. But anyway, so let me share the screen here. And then, okay, so can everybody see this? Can you see this? Yeah. Okay, so so I'm very happy to give a presentation here at this One World Signal Processing Seminar Series. So it's a pleasure to talk to you about this new research topic that we're looking into, which is learning higher order interactions from data. And more specifically, we will focus on so-called graph Volterra models. And I would like to acknowledge, first of all, my student, Mario Coutinho. So he's basically the driving force behind this research. And also Professor Giannakis from the University of Minnesota and his collaborators, PhD students and postdocs. So, okay, so as we know, networks are kind of everywhere, right? We know that in email correspondence, you have networks which can be represented as graphs, and there the nodes could be, let's say, the email accounts, and the edges are communications between the accounts. You have that in social interactions, where the nodes could be the users and the edges are interactions between the users. Also in drug compounds, so the nodes could be different substances, and the edges would mean that these substances belong to the same drug or are used in a similar drug. Or authorship networks, where the nodes are authors and then edges means that they collaborated in a paper. But it's clear that in all these networks that they also exhibit some type of higher order interaction, right? For email correspondence, we know that emails, they have many recipients, and social interactions, people gather in groups. It's not just a pairwise interaction in many cases. Also, several substances can be found in a drug, or papers also have more than 2 authors in general. So we need some kind of description of these higher order interactions. And here in this talk, we try to figure them out from data, basically. So how can we learn basically such higher order interactions? And we want to do that in a kind of a principled, data-driven manner. So a principled way that is well expressible and interpretable. Right, so let me give an example of this musical interaction here. It's a favorite example of my PhD students. So you have some kind of a group of rappers, so the Wu-Tang Clan, let's say, but a reborn version of that. And all these rappers here, they have certain attributes, certain features, maybe the type of song that they like to sing, or the type of instruments that they use. And then the question is, okay, based on these features, can we figure out, right, who is interacting with who? So that would be, let's say, the classical link learning, or link prediction, or link identification, if you want. So you could say that, okay, we might have a link between node 3 and node 4, but the link between node 1 and node 3 might not be active. So we want to figure out from the features who is collaborating with who, but in a pairwise way. Right, so that's basically the classical link learning. So if we want to state this in a more rigorous way, so you could say that we're after basically a graph. We know the set of nodes V, and we're after the set of edges E. So maybe we observe a subset of the edges. So that's here E observed. And we also have all these attributes, all these features related to the nodes. And from those, we want to basically learn the missing edges. So this appears basically in topology identification, where often in topology identification, you don't have any observed edges, and you just want to figure out all the edges from the features. But also in link prediction, the observed edges are basically the edges that happened in the past. So those would be the collaborations, or the pairwise collaborations of these wrappers from the past. And then we want to predict who is going to collaborate in the future, and those would be the missing edges. So this kind of problem statements, we call it learn, but it kind of stands for both topology identification as well as link prediction. And there's many approaches that people have developed: scoring methods, correlation, partial correlation networks. It's very popular. Regression-based methods, also graphical models are actually they date from the 70s with Dempster. Hypothesis test methods, and more recently then also a lot of graph signal processing methods that have been developed to figure out what are the links in such a network, learned from the features of the nodes. But in all these cases, yeah, we are dealing here with pairwise interactions. And we want to extend this basically to higher order interactions. So the question is, how can we do that? First of all, what are these higher order interactions then? So for this specific music collaboration example, so in that case, the higher order interactions would then be basically not the pairwise interactions, but which larger groups of collaboration, which larger groups are going to collaborate. So that's then the unknown, right? So it could be that node 5, node 4, and node 3, that they are going to collaborate. Sorry, am I drawing now? Or?
Yes, I can see the drawings.
Okay, yeah, I'm not doing that, I think, because I don't know. Anyway. So the question is, okay, then we have larger groups that we want to figure out. So not only pairwise interactions, but we want to see basically groups of people that we want to learn from the attributes that are going to collaborate in the future. But then the question is, how do we represent such higher order interactions? Again, there's many ways of doing that. You can so you can use, for instance, hypergraphs, where edges don't just join two nodes, but they join multiple nodes. Tensors is also very popular, right? So you know that the graph can be represented by an adjacency matrix, where the entries basically tell you which two nodes are connected to each other. But in a tensor, so you can have higher dimensional matrices basically. There, the entries, they represent multinodal interactions basically. So a three-dimensional tensor could represent basically groups of 3 nodes that collaborate. 4-dimensional tensors could represent groups of 4 wrappers that collaborate, and so on. Then you also have these abstract simplicial complexes, which basically contain a hierarchy of fully connected subgraphs. And there's also projected representations. Actually, we will come back to that later on when we talk about link prediction. And there's also many others that are here in a smaller font, which we're not going to go into details. But the problem with, or the pitfalls, let's say, with these type of methods is that they don't directly, or they don't always directly make use of the feature data of the nodes. They're not always data driven. And they often also make use of prior information of the structure, let's say specific motif structures and so on. And it might also be that certain physics-based assumptions that they don't hold in those type of models. So we want to make a modeling tool where we can directly make use of the data, of the features. And we want to have a model that is expressible, where we clearly see how the higher order interactions can be modeled and that can be interpreted in a good way. So that's what we're after. And what we go for here is basically a combination of two types of models that are very popular. So the structural equation models, which have been very popular in regular, let's say, link estimation, so topology identification, so pairwise interactions. So they have been very successful for that. So in those type of models, you're going to basically express the feature on the ith node here as a linear combination of the features on all the other nodes. So those are the xj's here. And they are just expressed by a linear combination. And the aij's, the non-zero aij's would be, let's say, the links that are active. So if an aij is, let's say, non-zero, then you would have a link between I and j. You can also have some kind of exogenous variables on top of that, so that's possible. But if you don't have this term, then you have kind of a self-driven model, right? So in a vector way, this would simply be x, vector x is equal to a times x, where a is the adjacency matrix then. So the adjacency matrix basically tells you how these features are linearly coupled. So without this term, you can model a kind of a self-driven behavior in this way. And although, of course, the linearity here is limiting, but it has been extended also to capture nonlinearities. Professor Giannakis has been working on that, for instance. But these are not the type of nonlinearities that allow you to do higher order link prediction or interpretability. So we want to extend basically the structural equation models to some higher order, where we can include some terms that are related to higher order interactions. And the Volterra series are useful for that, because they have been widely used for modeling nonlinear dynamics, higher order dynamics, but usually in time, not in a graph domain. And they give certain theoretical guarantees. So we would like to extend basically such a Volterra system from the time domain to kind of the graph domain. And a Volterra system also is often, let's say, input-output. So it's not self-driven. So we have inputs x and we have output y. And it looks a bit like this. So we have capital P terms. So that's the capital P is the order of the Volterra series. And so for small p equal to 1, we just have a linear combination of delayed versions of the inputs, right? So this is a classical delay line filter. But for small p equal to 2, we will look at linear combination of products of delayed inputs, right? For P3, we will have linear combination of products of 3 delayed inputs and so on. So this gives you all the higher order terms, right? But these are combinations of delayed or products of delayed inputs. Now, instead of these delays, we want to kind of extend this to the graph domain. So somehow we want to make a blend of that. And we want to make the Volterra series self-driven so that we have something related to X here as an output also, like we have in a structural equation model. And we want to go from time domain to the graph domain. So that's what we are trying to do to model the higher order interactions. This as an alternative to all these other ways of representing these higher order interactions. So, and the key idea is there that we try to describe the ith nodal feature. So there's one node that we focus on, the ith node, for instance. We try to express that in terms of so-called a set of subsets of nodes. So what are these subsets of nodes? So one subset of nodes is depicted here. So there if we focus on the ith node here in the center, then we will look at all the individual nodes that are somehow related to this ith node, whatever that means, right? So from the data, we want to look here for pairwise relationships between different nodes and the ith node. Right? Another subset of nodes is this one, where we want to see how two nodes jointly are related to the feature of the ith node. And we want to look for all the possible pairs of nodes that are interacting with this ith node. And we do this for every node. So not only for the ith node, but we do this for every node. And as you can see, so sometimes you have two nodes here that are, as a pair, they are interacting with the ith node, but it doesn't mean that they have necessarily pairwise interactions. It's basically the data that should tell us that, whether if two nodes are interacting, does it also mean that they individually interact? Often in many data sets, this will be the case, but the model doesn't necessarily enforce that. So basically what this means is we have this set of subsets of nodes, which we indicate with SPI. So it's basically a union of capital P sets. So it's similar to the Volterra structure, actually. So P1 is, let's say, is the set of all the individual nodes that collaborate with node I, or that are related to node I. For small p equal to 2, you have the set of all pairs that are related to node I. For P3, you have all the triplets that are related to node I, and so on. And their number is given by this capital L sub p. So every one of those sets is a union itself, right? And we want to express now the feature on node I as a function of all the other features, but also based on the structure of set of subsets that we have. So all the, let's say, the subset of individual nodes related to node I, the set of pairs related to node I, and so on. Right? And we do, and this will be a nonlinear mapping, and you can already expect now that what we're going to use for this nonlinear mapping is going to be a Volterra-like structure to indicate this mapping. So we first of all absorb this set dependency in the subscript I. And then we express this function like this. So we have a constant term, and then we have a superposition of capital P terms. So we have for every, so capital P is the order. So for every small p, we have a separate term. So for small p equal to 1, we will have, again, a linear combination of all the nodes that are all the individual nodes. So function of the individual nodes that are interacting with node I. For small p equal to 2, we have a linear combination of all the pairs of nodes that are related to node I. For small p equal to 3, we have a linear combination of all the triplets that are connected to node I, that are related to node I, and so on. And what do we take a linear combination of? Well, it's not the nodes themselves, of course, but it's the features on these individual nodes, or on these pairs of nodes, or on these triplets of nodes. And through a nonlinear function that is supposed to be permutation invariant. So in the standard Volterra, this would be a product of the XQs, but it doesn't necessarily have to be. It can be any nonlinearity that is permutation invariant. Right? And we have a superposition of those nonlinear terms. Right? And so these H's basically, they tell us how strong this interaction is. This interaction of individual nodes with node I, or the interaction of pairs of nodes with node I, or the interaction of triplets of nodes with node I. So these H, L, P, sup I, they basically tell you how strong the interaction will be. Now this model is for the case where we already assume that we know this structure, so that we kind of know what is this structure, right? And we only include the terms that for which the structure is available. Now, as I told you, we want to learn the structure from data. So we have the features available, but we don't know this set of subsets. So what we're after is actually this set of subsets. So what we will do is we will actually expand every one of these Volterra modules fully. We will fully expand it, including all the individual nodes for small p equal to 1, or all the pairs of nodes for small p equal to 2, or all the triplets of nodes for small p equal to 3, and so on. Right? So in practice, we have this fully expanded Volterra module that we have here. Right? So where now these sums don't all go over the active collaborations, but they go over all possible combinations of nodes. So for small p equal to 1, it goes over all the nodes. For p equal to 2, it goes over all the pairs of nodes. For p equal to 3, it goes over all the triplets of nodes, and so on. And then the non-zero coefficients that we will have here, they will tell us which are the active sets. So which are the active sets that are collaborating with node I. So again, this is kind of a model only for node I, right? We can do this now for every other node, and we can jointly solve this from the data. And then we know for every node, what are the different subsets of nodes that are related to the feature of that node. And how to solve this for the coefficients? Yeah, this is a simple sparse regression. So I'm not going to go into details. So you can do some kind of a sparse least squares problem that you can solve. And you can add certain constraints if you want. So as I told you, we assumed here that you can have, for instance, a pair of nodes here on the top collaborating with the node I, without having the individual nodes necessarily, both of them collaborating with that node. But you can put that as a constraint also if you want to look for those type of structures. So it depends a bit on the application, what you want to do there. But the model itself is very, let's say, general. So in that sense, it just looks at which individual nodes, which pairs of nodes, which triplets of nodes are basically related to the node I, and it doesn't put any extra constraints on that. So that's basically the type of model that we wanna use in certain applications. And one application is actually topology identification. So can we use this type of model now for topology identification from nodal attributes? And the specific application that we look at here is the one for power grids, so distribution networks, which often have this kind of tree type of structure. So you have certain buses. So the nodes in this case are these buses. So you have a parent bus here for node N, and then you have the child N, and then you have the children of node N. So, and it typically has this kind of tree structure. And now the question is, can we identify this kind of tree structure from the node voltages? Because it turns out that if you express the node, the voltage of let's say node N here, then the physics tell you that this can be modeled in this way, as you can see in the equation here. So the voltage on node N is the voltage of the parent node plus some kind of nonlinear function of the voltages of all the children. So this is the so-called nodal voltage nonlinear branch flow model. So this is what the physics tell you. And now the question is, can we now from the voltages themselves, and based on this model, derive what would be, let's say, the tree structure in your distribution grid? So that's basically what we try to do. And what people have done in the past is they try to linearize this model somehow, and then solve it, and then find what is the tree structure related to it. But that gives you a suboptimal performance. So this nonlinearity is important. So only linearizing it is not enough. And it turns out that if we use a Volterra kernel basically to model this nonlinearity, then we can get a very good performance. So we try to here focus on these nonlinear models, such as the Volterra model that we just proposed, in order to figure out what is then the network structure here. So instead of, let's say, this is the physics model, this is the actual relationship between the voltages, but how we will model it is through this kind of, again, self-driven graph Volterra model, where we have a linear term that includes the voltages of all the other nodes. So again, we focus on node N, and we have now here a linear term that includes the voltages of all the other nodes, because, okay, we don't know yet who is the parent or who are the children. We know that in the true model, there is a linear term that involves the parents, and there's also linear terms that involve the children. So that term is definitely there. And then you might have higher order interactions between pairs of nodes. Again, so this is a sum over all the pairs of nodes that you have, except for node N, that or actually N is included here. So it's the data that will tell you then whether N should be included or not. So it's a linear combination of all the possible nodes, of all the pairs of nodes. So we restrict ourselves to this kind of second order model. And if we try to indeed now solve this from the data, then actually it's the first order model that will tell us which are the pairwise links. So these are in green dashes here, you will see the pairwise links. So the non-zero coefficients here for the first order term, they will tell you which of the links are actually present in your tree structure. The non-zero second order coefficients, they don't represent actual physical links, but they are more there to see which are the voltages of the children are interacting with each other related to node n. So those are the red circles there. That doesn't mean that they have a physical connection, because we know that the structure is a tree structure. So we're gonna, let's say, learn both these first order and second order coefficients, but in practice, to figure out what is the tree structure, we only focus on the first order coefficients. But it's important to take these second order terms into account, because that gives you a better model than also for the first order coefficients. Just ignoring this term is not a good idea. Then you don't get a good estimate. So you basically use this second order term here to enhance the topology identification task of the first coefficients. So it's not really that these red circles here that mean that you have a closed triangle then in your network. That's more on an abstract level. You have that indeed, but the actual physical links are then only between the parent and its children. So that's the constraint here, that we know that it's a tree structure. And if we apply this to some data, so this is the SCE 47 bus distribution grid that many of the existing papers are using. So it's some real data. And we compare this to different baselines. Linear PC, a multi-kernel PC, and some concentration matrix method. And you see that the proposed method with the self-driven graph Volterra kernel really outperforms all the other methods. So this is here the receiver operating curve, so the ROC. So this is, let's say, you could say the true positive rate and the false alarm rate. So the red one has a much bigger area under the curve than the other methods. So it seems that this is a very good way to let's say, model this nonlinearity in these distribution networks. Another application is prediction. I talked to you about that. So there are cases where already some edges are known and you want to predict the missing edges. And these edges that are already known, they usually come from the past. So you know some past interactions between certain groups, and now you want to predict what are going to be the future interactions. So again, in this example of music collaboration, suppose that you know already that there are some songs between these different rappers. So we already have, let's say, 4 songs that are available. So then the question is, who's going to collaborate next? What is going to be the next collaboration, right? So which 3 or 2 or 4 rappers are going to collaborate next? So that's the type of higher order link prediction problem that we are looking at here. So in this case, there's not really features. It's actually the measurements or these joint works. In the past, we had as measurements the features of the rappers, what type of song they like, what type of instruments they like, and so on. But here we don't have those features. The only measurements that we have are, let's say, the past links. So somehow we have to also turn that into actual vector type of measurements. So the measurements are actually what we can call simplices. So every simplex is basically a set of observed nodes that collaborated at a certain time instance. So we have, let's say, song 1 being released at time 1. So that's 2 rappers collaborating. So that's our measurement S1. And then we have at time T2, we have also 2 rappers collaborating. That is measurement S2, and so on. And the question is, what's gonna happen next, right? Who's going to write the next song together based on this information, right? So that's kind of complicated. So to make it a little bit simple, a lot of the literature is focusing on seeing whether an open triangle becomes closed. So what do I mean with that? Is that suppose that you have an open triangle, so you have 3 rappers, and you know that the 2 of them, all the pairs, they have been active in the past. So Ni and Nj, they collaborated in the past, and I and Nk collaborated in the past, and J and Nk collaborated in the past, but they never collaborated all 3 of them together. And now we want to predict whether that will happen in the future, right? So if you consider a certain set A of 3 nodes that are in this set of open triangles up to time instant t, is there going to be a time in the future where it's going to become closed, right? So that's often a kind of a simpler problem statement than in generally then in general figuring out what is going to be the next group of people that's going to collaborate. But it's still challenging, right? So, and what the existing methods, they are often scoring based type of methods. So what people have done there is for every open triangle, they compute some kind of a score, and then they rank the different open triangles by that score, and they select the highest score as being the candidates for being closed in the future. So you get, let's say, a score function based on different triplets. So where it's assumed that I, J, K is already an open triangle, and we compute some kind of a score for that. And how the score is computed, that depends on many different aspects. So depending on the, so some researchers like local score functions, others prefer some kind of global score function. And okay, I will go over a few of these possibilities now, before we discuss our approach to that. So in many of these scoring functions, they rely on a so-called weighted projected graph. So if you represent all the interactions by means of this kind of higher order graph here, where so we have all these simplices here, all these collaborations from the past. So the pairs of them, they can be represented with edges, like say the 1, 6 and the 2, 6, and those will be edges here, 1, 6, 2, 6. The triplets here, like the T5, the 1, 7, 8. So those will be closed triangles. So those are in blue. And you can even have tetrahedrons. So the 1, 2, 3, 4 here, that collaboration with the 4 is a closed tetrahedron. That's indicated here by the yellow numbers. So you can kind of make a sketch of this interaction graph based on all the past data, based on all these simplices. So, and whenever you have an edge here, it means that these two have been collaborating in the past. Whenever you have a closed triangle, it means that these 3 have been collaborating in the past. Whenever you have a closed tetrahedron, it means that 4 have been collaborating in the past, and so on. And now, because we like to work with graphs, we want to turn this into a graph. And what is often done is you just kind of project these filled structures into the edges of a regular graph. So we turn this into a regular graph where the weights of the edges will tell you how many times these two people collaborated. So you will see a weight of 2 here on this edge, because 1 and 3 have collaborated twice in the past. And there's another edge where this happens. So you kind of project this kind of complete higher order interaction graph into a 2-dimensional, you could say, weighted graph, where the weights of the adjacency matrix tell you how many times that pair of nodes has been collaborating in the past. And then based on this weighted graph, people start computing these scoring functions for the triplets. So you can see in that graph, of course, whether there's triangles or not. And for all of these triangles, then people compute scoring functions. So it could be the geometric mean of the weights of the weighting matrix on all these edges between these 3 nodes. You can look at a function of the one-hop neighbors of these 3 nodes, I, J, and K. So here you get the size of the intersection divided by the size of the union. So that's some kind of Jaccard coefficient. You can even derive from the weighted adjacency matrix some kind of random walk adjacency matrix, and then some kind of a shift operator that represents some kind of the page rank model. So related to the probabilities of transition from one node to the other. And then again, there you can take a sum of the weights in this shift operator S here. That gives you some kind of global similarity function. You can even learn that function from the past data that you have, from these measurements Y that you have, all the simplices in the past. So there's many possibilities for the scoring function, but it's all kind of ad hoc. So it's not really clear which one is really better. People have been proposing these things, but it's not really very rigorously, let's say, proven what they actually mean, or what kind of performance you can expect from them. And there's a whole table on different kind of data sets where you can see their performance. So we try to compute these scoring functions based on our self-driven Volterra model. So can we somehow use that one to derive a scoring function? And of course we can do that. So we first have to turn, as I mentioned, these we have to turn these simplices somehow, these S of t's, into actual measurements, into actual features on the nodes, because we didn't have features. The only thing we had were these simplices. So what we do is we turn every simplex into a binary n-dimensional vector, which contains ones if these wrappers are involved in the collaboration, and zeros if they're not. Right. So that's very simple. So you turn this simplex into a vector. Actually, I have a picture of that later on, but at this point it's not yet there. But this is just an n-dimensional binary vector, which tells you at time instant t who was involved in the collaboration. And that's now our feature, right? Our feature vector for all the nodes. And we have many of those because we have many past collaborations. And I take that, so I take that into my Volterra model. So this would be the linear term. And I also include then a quadratic term, which these are just the products. But so this is like a Kronecker product, but dropping the redundant products there, because you get some symmetry. And this is then these are the second order coefficients. So we get a first order term and a second order term. And if you want to make this self-driven, then this, you would expect that here also you get something like STI. Remember, so I want to express actually the feature on node I as a function of the features of all the other nodes with a linear term and a second order term. But here we will follow kind of a logistic regression approach. So we will not put STI here directly, but we will put the probability here, or something related to the probability that STI will be equal to 1. We put that one there, given SIT, ZIT. So, and that allows you then to also, from the data that you have to estimate, let's say, these H's here. So the DC term, the first order term, and the second order term. By then, so instead of a regular regression, it will be then a logistic regression that you can do on that. And we can also put different constraints here in these terms now. I told you before, in the general model, we don't put any constraints. We don't care whether if we have a pair that collaborates with node I, whether both of the nodes collaborate with node I. That's not important, but we could put these constraints in the model. Here we will put actually particular constraints. First of all, we will remove everything that is related to node I, because I'm going to express something that's related to the feature of node I as a function of all the features of the other nodes. So if I is still included in ST here, then I'm going to have a kind of a trivial model. So we exclude those. And we also set to 0 all the coefficients that are not related to an open triangle, because I want to see whether an open triangle will become closed. So if that's my problem statement, I can set to 0 a lot of the coefficients here, because there might be cases that will never end up to a closed triangle because they're not even open yet. Of course, the ones that are already closed, I also include them in this kind of regression model, but I will not consider them because they are already closed. So there's no prediction in that case. Right, so we put some constraints on that, and then we do logistic regression. So that's basically how we solve that problem, the problem of figuring out whether an open triangle will become closed. So we will basically, from the initial connectivity, we will do that logistic regression, and we find the non-zero coefficients in our model. So the first order and the second order. We only included in these coefficients cases that are related to open triangles, because we want to see whether they get closed. And it's, of course, the triangles, the relations between triplets, we find those in the second order. So what we do after that, once we figure out the non-zero coefficients, we basically rank them, these second order coefficients, and we select, let's say, the triads with the highest absolute value of the second order coefficients. We say those are candidates that will become closed, because those coefficients there are somehow related to the probability that triplet. So because this basically tells you that the pair JK collaborates or is interacting with the feature of node I. So that coefficient is kind of related to the probability that this triplet will become closed given all the past observations of collaborations. So that's our working assumption here. Right, so we do the logistic regression, and then from the second order coefficients here, from this term, we pick the highest ones, and we do that for every node. and the highest one is then basically the triad or the triplet that we expect will become closed at some point. And if we apply that to some kind of standard data sets like the Enron email data set or the primary school data set, and we compare to many other methods or other scoring functions, we see that this kind of graph Volterra model does very well compared to these other scoring functions that were more, let's say, derived in some ad hoc manner. Here, the scoring function is let's say, clearly determined based on an interpretable model, let's say. Okay, so I think I can go to some kind of open venues now. So there's other things that you could check, that you could look at that we feel are interesting in this context. You could do something, some kind of tensor completion also for triangle link prediction. Because as I mentioned in the beginning, so you can represent higher order interactions also by means of tensors. So I can consider here a 3-dimensional tensor, and I could put in there, I can put to non-zero all the entries in that tensor, all the triplets that were collaborating in the past, right? So I just fill that up. I could even add a slice that includes also all the pairwise collaborations. So I have kind of this 3-dimensional sensor, which has dimensions, number of nodes. Here we have number of nodes plus 1, because I also include the pairwise as an extra slice. And then you could do some kind of low rank matrix completion to see, if you extend this to a low rank structure, what would be the highest triplets that are appearing after this kind of tensor completion, to see who's going to collaborate, which triplet is going to collaborate in the past. Another approach is that instead of this kind of page rank model, that you could consider a more general so-called graph, what they call graph filter and graph signal processing. So I could take any type of polynomial in this kind of random walk shift operator instead of just the classical one that is used in PageRank, and then also derive a scoring function based on that. That's also a possibility. Something that is also interesting is that we could model maybe the simplices as some kind of correlated point process. As I told you, every simplex can be represented by a binary vector. So this here means that at time instant t1, the first 4 nodes collaborated, right? This means that at time instant t2, node 1, node 3, node 5 collaborated, and so on. And now I can view this as kind of a vector process, right? st1, st2, and so on, as kind of a point process, like a Poisson process. And I could try to model that based on the past information, and I can then do some predictions about the future. What is the probability that, let's say, node 1 and node 2 are going to collaborate in the future, and so on, based on the correlations that I can figure out. Because all the existing methods, even our method on the Volterra, we don't really include the time domain there as in our dynamics. The Volterra is not in time; it's a Volterra in the graph domain, right? Even in our approach here. So we just view the time domain here as different realizations of our process, but we don't have a Volterra here in time. You see, for every equation that we have, the t is fixed. So we don't take into account correlations over time. We view these simplices as just different realizations of the process, as different features, you could say, of our nodes, and not as a process in time. While the point process here, you would really take the time domain into account. So that's why, that's also something that we're looking at right now, whether we can derive the link prediction also using this approach. So to wrap up, so I've told you that in many cases pairwise network modeling is not enough. There's many applications where higher order interactions are important, even if it's only for improving, let's say, the estimate of the pairwise interactions. It might be useful to include these higher order terms. We saw that in the smart grid application. And so we model the higher order interactions by a combination of structural equation models and Volterra series. So that allows us to express these higher order terms in a good way and interpret them. So I told you, like in the smart grid application, so including these higher order interactions can advance your topology identification result. You can also use it in higher order link prediction directly, because your second order terms give you an idea of what is the probability that those triangles will be closed in the future. Of course, there's a complexity issue. That's why we only focused on the open triangles. So we set all the coefficients to 0 that are not related to open triangles. Otherwise, we get a huge problem, especially if you have thousands and thousands of nodes. So that's why, yeah, the problem of going from an open to a closed triangle limits your complexity a little bit, but it's still kind of challenging. And as an interesting future work, yeah, we think that looking at these simplices as a spatial temporal point process could be an interesting future direction. So okay, so that concludes my my presentation. So I think I'm more or less on my 45 minutes. So any questions?
Oh, yes, I think there is so there's actually one from myself, and that is actually very similar to what Francesco just asked. So
Okay.
in the applications, we are you're basically looking at the case when the G function is like a product. And have you tried some other choices, and what are those other choices?
Yeah, so as far as I know, I think we only looked at the product, yeah. But yeah, let's see where. Yeah, so at least in the distribution network, we looked at the product. I think, yeah, and also in the link prediction or triangle prediction, we looked at this Kronecker product. So that was also a product. Yeah. So yeah. So what could it be? Of course, you could take a product of logs or something like that, right? So
yeah.
that could also be so. I mean, I'm just. I'm just thinking now out of my head what could be possible, other possible functions. But yeah, it could be something like that, right? But okay.
So one other option is some exponents of the product, or product of the exponents of these VIs, right?
Yeah, like I said, so it could be a product of nonlinear functions of these VIs, right? So that's something that.
Yeah. And do you think there will be some effects on the performance, like if we use a nonlinear functions on the
So it depends. I don't remember exactly what was the let's say what was the actual model. So I think we got it from the actual model, because in this actual model, I think there are some products between the children. So that's why we stick to just products. So I think because we have here a model coming from physics, so you could look at that one to see what could be good nonlinearities. But you're right. I'm sure the performance will be influenced. So it's you have to kind of check whether what to use there. It's more like a trial and error, I think, here, unless the physics model already tells you what you should use.
Yeah, and then I think next up we have a question from Ken. So maybe he can unmute himself.
Yeah, perhaps I'll also combine the latest question I put there. It's a very general question, not necessary just for graph. Now, a traditional wisdom is that Volterra can overfit because you have too many parameters. Now, so now, of course, traditionally, we don't have sparsity or low rank or stuff like that. So I guess it's really important that we need to use sparsity. All right.
Yeah, sparsity and like I said, constraints, right? So like, look, I mean, if the problem is really predicting whether an open triangle is closed, so then, for instance, I don't know if I have an example of a graph here where I can say that. Let's see. But so, for instance, if you have, or here in the prediction, I think here's so for instance here, so for instance, if you look at 3, 9 and 3, 5, so 3, 9 and 5, they're not even open triangle, right? So I'm not going to predict whether 3, 9 and 5 are going to be closed in the future, because they're not even open. So that coefficient I already set to 0 from the beginning.
So simply speaking, we still need to use a lot of domain knowledge of knowing application to save the day.
Right. So it's your past information that can tell you that. That's why we don't want to go for the more general problem, who's going to collaborate at any size, so which pair or which triplets. So we want to restrict the problem statement, because that allows us to simplify the complexity, and like you said, to prevent overfitting. So that's a good point.
And then, yeah, I mean, now the related question that I have is that, of course, this question is probably the student who will know best or the research staff would know best. Now, in theory, you can do whatever higher order Volterra series you like, right? But from second order to third order to fourth or even beyond, not only that you have so many parameters, but you could as well do bad thing like overfitting, even though you put sparsity. Or we can make the story even more complicated because when you do sparsity, you're going to have a regularization parameter for L1 or stuff like that to tune, right? So there comes an ambiguous question that every time you have a higher order, then you have to retune your parameter for sparsity. So perhaps my interest is your experience on that. Should I use, is it okay I use a higher order, or I still want to be a little bit more careful?
Yeah, it's well, yeah, it's a bit like you can view this as a Taylor series expansion, right? So there you have the same problem, right? So in your Taylor, you want to model a function with the Taylor series expansion. Up to what order are you going to do that? I was discussing last night also with my student. So he said also that you could start from a higher order because the higher order, let's say if you have non-zeros in your second order term here, so this is like a second order derivative. So probably then you should also have a non-zero in your first order derivative, right? Or so you can already kind of first try to figure out these higher order terms and use that one to put extra constraints on your lower order terms and do that kind of in a sequential way. And so in your first step, you don't care about the lower order terms or something like that. But again, I think the solution is, yeah, putting some kind of constraints there, or constraints in the sense that I'm only going to look for a triangle if I also assume that the edges are there, right? So that there's actually a constraint relating the first order and the second order term. We were never really using that in our applications. So like I said, it could be that there's a non-zero term here, that two nodes are interacting with the node I, but that separately, that they're not, both of them might not be interacting with node I. So the two coefficients here related to one coefficient there, they might not all be jointly non-zero. So you can enforce them to be jointly non-zero. So there might be, in this Volterra structure, there might be different types of structured sparsity constraints that you could include. Next to just saying it is sparse, you could say, no, there's some kind of group sparsity also. Because I could enforce that if I have a triangle, I should have also all the edges there from that triangle, right? So, and that you could enforce as well.
Agree. Thank you.
But yeah. But I think most of the literature is also involved in let's say triangles. So that's why most people focus on second order and yeah.
So we also have a question from Zhonghui about the logistic regression part. So Zhonghui, do you want to unmute?
Yeah, I'm not sure if my question is appropriate. So here these ST are given or not? So
yeah, so the SPs is the past data, right? Yeah.
Okay, so in the history, we do know that which three nodes they are.
Yeah, so yeah, who was collaborating? Yeah, so we know who's collaborating in the past. So that's what we use for the regression. So and
okay,
then
no, I understand.
Yeah, and then we figure out, we look at the highest coefficient. So the strongest open triangle is probably going to be closed at some point. So that's basically the idea behind it. So this, because if you have three very strong interactions in an open triangle here, so if we have three very strong interactions here, then probably that's going to be the first one that's going to be closed at some point. So that's the idea behind it.
Okay, thank you.
Yeah.
So next we have a question from Michael. So Michael, would you like to unmute yourself?
Yeah, thanks, Toh. Thanks for the talk. Quite interesting. I have a high-level question with respect to neural networks. So in graph neural networks, you basically take a sum of inputs and you apply a nonlinear function to it, and you tend to do this sequentially. You're sort of doing the opposite. You're taking a sum of potentially nonlinear terms, in your case, polynomials. So have you thought about potential connections or yeah, cases where this sort of, one could inform the other or something like that?
Yeah, that's a good point. Yeah, Let's see. Yeah, we haven't directly thought about it, but in a way, yeah, you could say that this is kind of a. Let me see if this. Yeah, so you could view that the first order term is like a graph filter, right? So what you could use in between layers in a graphical neural network. So it might be possible that you could extend your graph filters also to include then these kind of second order interactions there, so that you design this as being a graph filter in between your layers. Of course, in that case, we know which are the non-zero coefficients, because that's then what the graph is giving you. So we can have, let's say, a higher order graph neural network, you could say, where so then basically this would be the graph. So we run a neural network over this higher order interaction graph, you could say. So how do you do that? Okay, I think then in between layers, I need some kind of a Volterra, right, filter in between the layers, and then so that's actually a good idea. So I think, yeah, it's kind of a higher order extension in that sense, also for the graphical neural networks. Yeah. But here the focus was on topology ID. But if the graph is given, then you could view this as kind of a higher order filter on a higher order graph.
Yeah. So so next, maybe Fan, you can unmute yourself.
Okay, yeah, thanks, Geert, for this wonderful talk. I have just noticed in recent years that there are quite some work from the Machine Learning Society that actually adopted deep neural networks to detect arbitrary order interactions. For instance, I list some references by Zhang and Liu from I think USC, right? I think the idea is actually very interesting. They detect higher order interaction from the neural network ways, and this idea could also be extended by using graph neural networks. But we know that the major drawback for neural network is the black box nature. I wonder if you have noticed this works and have any idea how to incorporate this interpretable GBM into the black box, so that we have sort of a gray box in the end with good accuracy and also interpretability. Okay, that's my question.
Yeah, thanks for the question. So yeah, since I have not been very deeply involved in this research, so my student probably knows better. So I don't know whether he looked at those deep networks, but yeah, so I cannot directly answer that question, but it's a good point that we should also look at those more advanced, let's say, methods, and yeah, I think they might be related to this kind of machine learning approach where you learn the scoring function. I'm not sure what they exactly do, so it could be that it's a bit related to that one, where you kind of, because this looks like a learning problem over this graph W, which was this weighted projected graph. So it could be that they focus on that one.
Yes, I think yeah.
But thanks for the reference. So we will check it out. Yeah.
All right. So so is there other questions from the audiences? So if not, let's please join me to thank the speaker again. And
yeah, thanks. You're welcome.